Analytical Chemistry 1, Lesson 29. Let's take a look again at weak acids and bases. Now, even though an acid or base is identified as being weak, that does not mean its acidity or basicity is necessarily modest. It only means that it is not fully dissociating in water. As such, we need to take account of its equilibrium. Here's what we have learned about them so far. The weak acid is characterized by the dissociation reaction. We call its equilibrium constant the acid dissociation constant. On the other hand, when a weak base dissolves in water, it reacts with the water to capture a proton and leave a free hydroxide in the solution. We call this the base hydrolysis reaction. Hydrolysis because it reacts with water. Its equilibrium constant is known as the base hydrolysis constant. Recall how these reactions are always based on an acid-base conjugate pair. A- is the base conjugate to HA. BH+ is the acid conjugate to the base B. The conjugate base of HA is really just another base. We could add it to water and it would hydrolyze just like the base B. Its reaction is the same, and we can write out the similar base hydrolysis equation for it to happen. But now look what happens. We can multiply the two equilibrium expressions together. Now note that it must be the equilibria for an acid-base conjugate pair, not just any acid or any base. But when we do that, things cancel, and we are left with just the product of hydronium and hydroxide, which is, of course, just Kw. Ka times Kb equals Kw. This is a relationship that is worth remembering. Let me offer a little interjection at this point. I've been writing the acid dissociation reaction as this, implying a free proton, H+, is released into the solution. In other places, you may find the same reaction written like this, where the H+ ion is seen to associate strongly with the water molecule and the hydronium ion is written as H3O+. Is one of these more accurate than the other? Well, it is true that when the free proton is solvated in water, it organizes the water molecules around it. Writing it as H3O+ is an attempt to acknowledge that interaction. The issue, however, is that it is likely even more extensive than just one additional water molecule. If you recall back when we were talking about an ion's activity, we needed to include each ion's hydrated diameter in order to use the extended Debye-Huckel equation for its activity coefficient. The humble hydrogen ion was actually one of the largest hydrated ions, much larger than even some complex molecular ions. The proton itself was only about 85 femtometers in diameter, but its hydrated diameter is about 900 picometers. Some suggest that a better description of the hydrated proton would be having it associated with 4 water molecules, H9O4+, so you might feel a need to write the reaction like this. So which equation is more accurate? Well, that depends upon what you're trying to achieve. For the majority of our work, we are just trying to keep track of atoms as they react. The first equation is just fine. But others feel a need to remind us that it is hydrated and so often use the second equation, and that is also fine, but it does not add anything new to the stoichiometry of the reaction. You will find people using both the first and second equations, and both are acceptable. But if anyone tries to tell you that the second one is the only correct one, well, no. It's more complex still. The third equation is more correct, and there is theoretical work to suggest even more water molecules may be involved, perhaps as high as 20 water molecules involved according to some research. And the number of water molecules is in fact continually changing as they move in and out of the hydration atmosphere around it. Now that's a worthwhile problem to study, but not one that helps us with our analytical chemistry problems. The purpose of these equations is to allow us to keep track of stoichiometry, and the simplest one does that just fine. The equilibrium constants are often found tabulated for the various reactions. Their values span many orders of magnitude. Because large variations in exponents can be encountered, the data is often presented as pKa or pKb. The p function, again, is just the negative base 10 logarithm of the number. The reverse operation, change its sign and exponentiate to the power of 10, can't produce the Ka or Kb value back. We can operate on Kw to get pKw. And the relation we derived before can be written in these terms as pKa plus pKb equals pKw. They are added together because that's what you do when you take the logarithm of the product of two terms. Here are some examples. Acetic acid has an acid dissociation constant given as pKa equals 4.756, which converts to a Ka of 1.75 instead of the minus 5. As an aside, these numbers are for acetic acid in a solution with an ionic strength of 0, an extremely dilute solution. In a solution with an ionic strength of 0.1 molar, its pKa is 4.56. You see, activity does make a difference, so as your work becomes more sophisticated and complex, plan on using it. We just won't use it here unless it's explicitly called for. 1-naphthoic acid has a pKa of 3.67 and a Ka of 2.1 times 10 to the minus 4. Now, can we compare these two acids? Is one a stronger weak acid than the other? Which will produce more hydronium ion for the same formal concentration? Well, let's compare 1 millimolar solutions of each. Recall that we can use the quadratic solution for these equations, for these situations. Ka is not too small and the formal concentration is not too small. Recall that when we are saying not too small, we're comparing it to water. Here's the quadratic formula expression. We only use the root that employs the plus sign for the radical because that is the one that would be positive and the only one that makes physical sense. Let's compare 1 millimolar solutions of each acid. Plugging in the numbers gives us 1.24 times 10 to the minus 4 molar for acetic acid and 3.45 times 10 to the minus 4 molar for the 1-naphthoic acid. The naphthoic acid solution is more acidic. We can say that naphthoic acid is a stronger acid than acetic acid. The solution pH values are 3.907 and 3.462. It has a larger value for Ka, so the larger the Ka, the stronger the acid. And because of the form of the P function, the smaller the pKa, the stronger the acid. The same thing is true of bases, of course. Ammonia is a very common one. As a base, it would react like this. And we would write out the equilibrium expression for Kb. But then we might run into a problem. For instance, you might look up ammonia in the table in your textbook and find not Kb, but rather a value for Ka. So what gives? In order to simplify the tables, authors commonly report just the Ka or pKa for the conjugate acid form of what is being tabulated. So under ammonia, we find pKa equals to 9.245. But this is for the conjugate acid ammonium ion NH4+. But remember our equation? Ka Kb equals Kw, or pKa plus pKb equals pKw. So we can quickly find Kb for ammonia as 14 minus 9.245 equals 4.755. And it is easy to turn this into Kb. Just take 10 raised to the minus 4.755, which is 1.76 times 10 to the minus 5. So what is the pH of a 1 millimolar solution of ammonia? We can again use the quadratic approximation solution. However, this time we are solving for hydroxide concentration rather than hydronium ion. We substitute for the formal concentration and this value for the base hydrolysis constant and obtain 1.24 times 10 to the minus 4 molar for the hydroxide concentration. Well, it's easy to turn that into POH, and it's 3.906, but we want to know the pH of the solution. There's that same relationship to pKw. We easily get 14 minus 3.906 equals 10.094, which is the pH of the 1 millimolar solution of ammonia. A very basic solution indeed.